Hello, I am Yusuf Shakil, and together with my group mates, Muzamil and Hanif, we will be talking about the Lattice-Boltzmann method. I will be talking about the introduction to the method and its historical perspective. Muzamil will talk about general principles and governing equations. Hanif will be talking about, will be giving a hand calculation example as well as a numerical example. And I will wrap up by talking about field applications. Let me start by talking about this method, which is a compromise between the micro scale and the macro scale. At the micro scale modeling, we're talking about the molecular level, which is never practical to model because of the huge amount of particles. There can be as much as 10 to the power of 26 particles in 1 liter of air. So, and these are governed by Hamilton's equation. On the other hand, on the macro scale, we have equations such as Navier-Stokes, which require an analytical solution, but we can also get numerical approximations via finite difference method, finite volume method, and finite element method. On the other hand, we have a marriage between the two, and we get the mesoscale, and we have a number of molecules whose behavior has been averaged, and we call these the nodes. And then a number of these nodes collectively give us the macro scale behavior, and we primarily use the Boltzmann transport equation to help us do that. So the Lattice-Boltzmann method originates from non-equilibrium statistical mechanics, where we have a dynamic lattice model, which we will be talking about later. And this has been discretized in terms of time, space, and velocity. And together with the Boltzmann equation, we get the Lattice-Boltzmann method, which gives us a very good approximation of the Navier-Stokes equation without requiring us to solve it analytically. So this method is very good for multi-phase flow. We can use very complex geometries, complex physics, and flow phenomena. It's very important to note that we can use it for parallel computing, where we break the problem down into parts and each solution is solved locally, and then we have a number of computers which are together solving parts of the equation of the problem in parallel, which really speeds up the process of getting a solution. Also, this method is applicable to microscale fluid flow, which is due to the origins of the method lying in the kinetic theory of gases. However, this method is very computationally expensive because of the large memory needs compared to traditional Navier-Stokes solvers. It cannot handle very low viscosities. Low and high resolutions cannot be coexisting, and it's hard to prescribe permeability and compressibility to the system. The Mach number needs to be less than cannot be less than 0.2, and it is inefficient for solving steady state problems because of the very slow convergence. It is different. Talk about the differences from computational flow dynamics. So in CFD is primarily Navier-Stokes equation, which is a second order equation of convection, whereas Lattice-Boltzmann method is a first order partial differential equation of advection. And in the Lattice-Boltzmann method, we have implicit discretization. Now I'll talk about some historical background starting from 1860, when we had the Maxwell-Boltzmann distribution, which was based on the kinetic theory of gases, primarily classical ideal gases. And this basically tells us that the distribution of particle speeds tell us about the speeds which are more probable. In 1872, we had the Boltzmann transport equation, which gives probability distribution functions of position and momenta of particles, which tell us about the physical and fluid properties of the system, such as momentum, heat, etc. Uh, there were two prototypes in 1964 and 73 respectively. The first one was the Broadwell, which was very basic, where the Boltzmann equation was solved for only 8 discretized velocities to solve some aerodynamics problem. Then we had the HPP problem in 1973, where we had a very basic square lattice. It was very anisotropic because of no rotational invariance, and um, the particles could only move in 4 directions. Uh, the main predecessor of the lattice Boltzmann method was the lattice gas automata of 1986, which was introduced by these 4 people, Frisch, Haslacher, Pamio, and Wolfram. This used a hexagonal lattice, which I'll show in the next slide, and the particles were modeled with discrete velocities, and they could only move to other lattice nodes. There was Boolean variables, which basically means like true or false, which dictated the particle position at the lattice nodes. This method was able to correctly model Navier-Stokes equations. In 1988, the lattice-Boltzmann method was introduced by McNamara and Zanetti, and this method fixed all the limitations of the lattice gas automata, which were statistical noise, inability to handle 3D problems, and viscosity limitations. The lattice-Boltzmann method uses square nodal lattices, which also allow diagonal movement, and distribution functions were introduced, which were a major breakthrough.
So in this part of the presentation, I'm going to be talking about the general principles of the Lattice-Boltzmann method. So before we talk about the Lattice-Boltzmann method, it's important to talk about another type of molecular simulation which we call the lattice gas automata. So the lattice gas automata is a type of a simulation where individual gas molecules are simulated over a discretized space and time. An example of a discretized space is shown here. So you can see that this space is divided into cells, and these arrows right here, these are individual gas molecules. They will move along these cells in the direction of their motion, and they will do so in fixed time steps, since it's a discretized space and time. So an example of a cell from the previous discretized space is shown here. So this is one unit of that discretized space. Each cell has certain sites which are shown here, these spaces right here. And these sites are where these molecules, the gas molecules, are located at. Now each site can either have a molecule, like shown here, these red arrows are molecules, or it can be vacant, like this site right here. And each site can have at most one molecule. So after each time step, the molecules will start to move to their neighboring cells. And one of two things can occur. Either the neighboring cells can be vacant, in which case the molecule will move on to just casually move on to the next cell, like shown here in A, or the neighboring cell can have another gas molecule there, in which case a collision will take place, like shown here in B and in C. So during these molecular interactions, the mass and the momentum are conserved. What I mean by the mass conservation is that the total number of molecules before and after the collision remain the same. That means the mass is conserved. And by momentum conservation, I mean that the total momentum of the system is conserved. For example, here in B, if we consider that these molecules have the same mass, and since they're moving in the opposite direction, their total momentum is zero, And even after the collision, since they're moving in opposite directions, their total momentum will be zero. The same is the case with with C, and with A, but here the total momentum is not zero, but it's still conserved. So for simplicity, the simulation is divided into two substeps: collision and propagation. So during the collision steps, the molecules which are at one cell, they will interact with each other, but they will not move to the neighboring sites yet. They will just collide, should we say. And notice here that this cell is not the same as the cell I showed in the previous one, which only had 4 sites. A cell can have any number of sites. So this is a hexagonal cell with 6 sites. So during collision, they will just interact but will not move forward. And the time of the simulation will not increase during this substep. And during propagation, the molecules will just move on to their neighboring site according to the direction of their motion, direction of the arrow, which are shown here. So they will move on to their neighboring sites. And during this substep, the time of the simulation moves forward by one time step. Up till now, we've only talked about the interactions of the molecules, but we're not really interested in those interactions. What we're interested in is the properties of the fluid that contains that molecules, the bulk properties, like the density of the fluid or the velocity of the fluid. So these microscopic interactions that I talked about earlier, these can be translated into bulk properties. So let's first of all start with the density. So if we assign a molecular density Ni to each of the sites in the cell, the macroscopic density of the fluid will just be equal to the sum of the total mass inside a cell divided by the total volume of that cell. So that will be just m into the summation of n across each of the links. So that will give us the total mass of a cell divided by the volume of that cell, which is just the density. We can do the same thing with momentum if we assign a velocity ei to each of the molecules. So the macroscopic density of the macroscopic momentum density of the fluid will just be equal to the sum of the microscopic momentum densities of each of the molecules across the site in a cell, which is given by this equation right here, where rho u is the macroscopic density, momentum density, and u here represents the velocity of the bulk fluid, whereas e is the velocity of the molecules. So now I'll talk about how we will go from lattice gas automata to lattice Boltzmann. So in lattice Boltzmann, we define a lattice space, which can be thought of as a collection of cells from the lattice gas automata. So here I have an example of the previous lattice gas automata grid that I showed. So if we take a bunch of these cells and we group them together to form one big lattice, this will be the lattice space, this will be one unit of the lattice space we will use in the lattice Boltzmann simulation. Now here, instead of talking about individual molecules on each of the sites, we will talk about the average number of molecules moving in that direction. For example, this arrow right here represents the average number of molecules moving towards the right within the cells these compromises of. And the same with this arrow, it shows the average number of molecules moving upwards or downwards, or this one towards the left. Here, you can see that the linkages, it has the same number of sites as the cell it comprises of. Here we refer to the sites as linkages usually. And an important thing to note is that since we're no longer talking about individual molecules, we use we use distribution functions for each of the linkages, which is represented by f. An example of a lattice Boltzmann lattice is shown right here. This is called the D2Q9 lattice. D2 meaning two-dimensional and Q9 meaning having 9 velocities. On this lattice, you can see that there are 9 linkages for each of the 9 velocities. So you have 1, 2, 3, 4, 5, 6, 7, and 8. And there's also one called F0 at the center. This corresponds to the molecules that are at rest and will not be moving during the propagation step. And each of the linkages has a distribution function attached to it, which is referred by F. So now, instead of using the lattice gas automator cells to discretize our system, we'll be using lattices like the one I just showed you to discretize our system. An example of doing that is shown here. This is our space, and you can see that we have divided these into the T2Q9 lattices like this. So like lattice gas automator, the lattice Boltzmann method is divided into two substeps, collision and propagation. So during the collision substep, the molecules interact together, but they do not move towards the neighboring sites just yet. And these interactions are predicted by some models, one of which I will discuss later on in this presentation. And at the start of each collision step, every link has a pre-collision value, which we will refer to as Fin, which are given right here, which means the incoming distribution functions or the incoming molecules. And after the collision, these are going to be converted into outgoing distribution functions, and their values will change according to the interaction between these molecules. During the substep, the time of the simulation does not progress. It will remain constant. So following the collision substep, we have the propagation substep. And during this substep, all of the outgoing distribution functions from collisions are just going to be transferred to the neighboring lattices. And the distribution functions from the neighboring lattices are going to be transferred to the cell of interest. So it will just be an exchange between neighboring lattices of distribution functions. The value of the distribution function is not going to change in this time step. So let's have a look at this example right here of a D2Q9 lattice system. So we can see that there are 9 distribution functions on this lattice of interest, and they're going to move to their neighboring cells, to their neighboring lattices, according to the direction of their motion. So for example, F3 is going to move to the right here to this lattice, where it will become the incoming population for the next collision step. So F7 is going to move to the top right, and F4 is going to move to the top, F1 is going to move to the left, and so on and so forth. All of these are going to move except for F0 right here, which is going to stay at the same position since we mentioned earlier F0 corresponds to the molecules at rest. They are not moving. So say we have a system in which the lattices have a length of delta x and a width of delta y, and the time step of the simulation is delta t. We can figure out what the velocity of each of the links will be. For example, if E0 corresponds to the velocity of the distribution function F0, the velocity is going to be 0, 0 since it's not moving anywhere. So F1 is the velocity of the distribution function F1. E1 is the distribution velocity of the distribution function F1. So we can see that this function moves towards the left, and it moves by a distance of delta x. And since the time is delta t, the velocity will be given by minus delta x over delta t. So F2 moves one step down in a direction minus delta y. So the velocity will be given by minus delta y over delta t. So this will be the same for each of these distribution functions. So except the ones on the diagonal will move in the x and the y directions as well. So they'll have two velocity components. We usually define a lattice such that delta x is equal to delta y for computational simplicity. And in LBM, we usually take our delta x, the space discretization, to be equal to 1, and the time step also to be equal to 1, so that our velocities will reduce to very simple ones and zeros. One final thing I would like to talk about is the boundary conditions. So a particular boundary condition I would like to talk about is the bounce back boundary condition. So consider the following arrangement here, and this is our cell of interest. So, like we said in the propagation substep, the distribution functions move from the cell to the neighboring cells, and the distribution functions from the neighboring cells will come into the cell of interest. So if we consider this cell right here, the distribution functions of F4, 8, 1, 5, and 2 are all going to move to the neighboring cells. F0 is going to remain the same, but F7, F3, and F6 have nowhere to go since this is a boundary right here. And similarly, the distribution functions from the neighboring cells are going to come in to fill in all of these locations except for 7, 3, and 6. So how we treat these cells is that we say that these cells will bounce back from the boundary back to their current location. So the F7, F3, and F6 are going to collide with the boundary, and they're just going to switch directions, and they will remain at the same place. Next, I'm going to be talking about the governing equations behind the Lattice-Boltzmann method. The governing equation of the Lattice-Boltzmann method is the Lattice-Boltzmann equation, which is a discretized version of the Boltzmann transport equation. So before I derive the Boltzmann transport equation, it's important to understand what exactly the distribution function is. So let's consider a packet of molecules with n molecules in it. And this packet is located at a position in space x, y, and z. And this packet has dimensions of dx, dy, and dz. And we're only allowing the molecules with a certain velocity in this packet. And that velocity is in between vx, vy, vz, and vx plus dvx, vy plus dvy, and vz plus dvz. So the molecular density within this packet will be given by a distribution function f, which is given right here. So this f is the total number of molecules per volume per velocity. So it's n divided by dr, where r is dx, dy, dz, into dv, which is, and v here is dvx, dvy, dvz. So this is the total volume molecules per volume per velocity. So the distribution function is a function of position, velocity, and time. And these are 7 variables right here, expanded. So let's say a group of molecules at position r and a velocity v are in a force field that has an acceleration of a. So after a period of time dt, and given that the molecules do not interact with each other, these molecules will move to a new position, which will just be equal to the old position plus v dt, and they will all have a new velocity, which will be given by v into a dt. And since we said that these molecules aren't interacting with any other molecules, the number of molecules at this new position will be the same as the number of molecules as the previous position right here. So the distribution function will be the same as before. However, in reality, the molecules do interact with each other, and when they do so, the distribution function is going to change. And the rate of change of the distribution function with respect to time is given by a collision operator, omega. So the left-hand side of this equation right here is just the derivative of f with respect to time. This is df over dt. And since this is a derivative of multiple variables, it can be expanded using the chain rule. So the expansion of df over dt is del f over del r into dr over dt plus del f over del v into dv over dt plus del f over del t. So this term right here is the change of position with respect to time, which is the velocity. And this term right here is the change in velocity with respect to time, which is just the acceleration. So when we put the acceleration and velocity into the previous equation, it reduces to this form. And this is the Boltzmann transport equation. Now we need a way to estimate the collision operator in the previous equation. So there are many models, but the most popular one is the Butnagar-Gross-Krug model, which is called the BGK model. And according to that model, the collision operator is given by minus F equilibrium divided uh, by some relaxation time tau. And this F equilibrium is given by the Maxwell-Boltzmann distribution, which is right here. And in this distribution, uh, rho, u, and t are the macroscopic velocities, density, velocity of the bulk fluid, and the temperature, respectively. K is the Boltzmann constant, m is the mass of the gas molecule, d is the dimension of the problem you're dealing with. For example, if it's a one-dimensional problem, the d will be equal to 1. If it's a two-dimensional problem, d will be equal to 2. If it's three-dimensional, d will be equal to 3. And this v right here is the velocity of the molecules, as opposed to this u, which is the velocity of the bulk fluid. So once we put the BGK collision operator into our Boltzmann transport equation, it reduces to this form right here. And this F is called the forcing term, which is dF over dV into acceleration from our previous equation. So this is called the discretized Boltzmann BGK equation. So the velocities used in this equation are continuous velocities. And it's really hard to solve a problem when we have a continuous set of velocities. So what we do is we choose a particular set of velocities and we discretize the equation over that set of velocities. So we write the equation for a distinct set of velocities, which we refer to as VI. So for example, if you're using the D2Q9 model, which we discussed earlier, these will be this will be 9 separate velocities as given by that model. And you'll have to write this equation 9 separate times for each of the velocities. So we can discretize our equation in time as well. So the left-hand side of our discrete Boltzmann BGK equation is this term right here. So this is the distribution function at the new position and new time minus the distribution function at the old position and time divided by del t. And this is a discrete time. So we can just write this with the superscripts n plus 1 for the new position in time and n for the old position in time. So the left hand side of this equation takes this form right here. Since we're assigning a time level to the left hand side of the equation, we have to do the same for the right hand side as well. So what we do is we take an arithmetic average of the right hand side between the two time levels. So simply put, that's just the right hand side at time n equals to 1 plus the right hand side at time n divided by 2. So that's just the arithmetic average of the right hand side between the two time levels. So once we do that, our equation takes this form right here. Now you'll notice that this is the variable we have to solve for, which is the distribution function at the next time step. However, this equation is not implicit. This equation is implicit in time, since we have another term right here, which has a time level of n plus 1. So we want to solve for fi n plus 1, but we already have an fi n plus 1 on the right hand side. So we need to convert this into an explicit form. So to do that, we introduce a new distribution function. Uh, called fi bar, which is defined by this value right here. And f bar n plus 1, all terms will be here will be n plus 1, and f bar at n, all terms here will be n. And we also define a new relaxation time, tau bar, which is just tau over del t plus 1 over 2. So once we make these substitutions into our original equation, the equation takes this form right here, which is a fully explicit form, and this is the Lattice-Boltzmann equation. So for simplicity, we divide the equation into two parts, collision and propagation. So notice here that this f right here, it's at the new position and new time. So what we do is we first just carry out the collision step, which is we compute the right hand side of this equation, but we do not put it in a new position in time. So it remains in the same position in time. We just compute the value just changes. And during the propagation, we just take this new value which we calculated, which we're referring to as f star, and we assign it to a new position in time. We've been only talking about the distribution functions, but what we're really interested in is the macroscopic properties of the fluid, like the density or the velocity. And these macroscopic properties can be found from these distribution functions. It's actually a reverse engineering problem. So the Lattice-Boltzmann equation can be shown through the Chapman-Enskog expansion, which I won't be mentioning here, but it can be shown to reproduce a given number of equations. And it depends on how you define your distribution functions and your forcing terms. So for example, if you want to reproduce the Navier-Stokes, these following identities must be satisfied. So that the rho must be equal to the summation of the distribution function at each linkage in a lattice. The rho into the macroscopic velocity of the bulk fluid should be equal to the summation of the distribution function into the microscopic velocity plus del T over 2 into the forcing term, and the viscosity of the fluid should be equal to the speed of sound squared into tau, which is the relaxation time, minus 0.5. So what I mean by a reverse engineering problem is, if you want to reproduce the Navier-Stokes, you'll have to use these identities in the Lattice-Boltzmann method, and that will give you the Navier-Stokes equation. So Cs, which I referred to here, is the speed of sound. And for an ideal gas, the speed of sound is equal to the Boltzmann constant into temperature divided by the mass of the molecules, mass of the gas molecules. And this is a constant for isothermal flow problems. And we also treat it as a constant depending on the type of lattice we use. Next, I'll talk about the discretized equilibrium distribution function. So earlier I mentioned that we use the Maxwell-Boltzmann distribution function for our equilibrium distribution function, but this is for continuous velocities. So in our Lattice-Boltzmann equation, we use a discrete form of this. And in the discrete form, instead of writing the continuous velocity v, we write vi, which is the discrete velocity. So once we plug that in, and we Taylor series expand the e term, we get this form of the equation right here. So all of this whole term is actually a constant. The velocities, the discrete velocities are actually set to be constants depending on the lattice you're using. So all of this can be treated as a weighing function Wi. So next I'm going to talk about the forcing term, the discrete forcing term in the Lattice-Boltzmann equation. So we said earlier that the forcing term is equal to the acceleration into the partial derivative of the distribution function with respect to the molecular velocity. So if we approximate the distribution function to be equal to the equilibrium distribution function in this equation, we can expand this derivative as written right here. This is just a derivative of the equilibrium distribution function with respect to the velocity. And this is the same equilibrium distribution function we derived in the previous slide. So once we expand this term, we put in the equation for the equilibrium distribution function. The equation takes this form right here. So if we ignore the higher order terms that are that have a order of the molecular of the macroscopic velocity squared, if we ignore all those terms, what we are left is this equation right here, which will be our equation for the forcing term in the Lattice-Boltzmann method. So this is actually not a bad assumption to make, since when we look at the macroscopic velocity and compare it to the velocity of the molecules, it's actually much smaller than the velocity of the molecules. So the terms of the order u square can be neglected easily. The last thing I will talk about is the relaxation time. So earlier I mentioned that for the Lattice-Boltzmann equation to be able to reproduce the Navier-Stokes equation, the viscosity should be equal to the speed of sound squared into the relaxation time minus 0.5. So if we rearrange this equation, we can get the relaxation time in terms of the viscosity of the fluid. And this is if you want to map Lattice-Boltzmann onto the Navier-Stokes. If you want to map it onto a different equation, then we will have a different expression for the relaxation time. So to summarize the entire process, the Lattice-Boltzmann equation is given over here, right here. It is divided into two steps, the collision step and the propagation step. The collision step is just this term right here, the right-hand side of this equation. And propagation is just moving that term onto their neighboring lattices while moving the equation forward in time. So the unknown to solve in this equation is this term right here. This is the distribution function for the next time step, which I've represented it as fn plus 1. So tau, the Fi equilibrium, and the forcing term can be found using the equations I mentioned before. The Fi at the initial time, at time n, which is this term right here, and also this term. This has to be initialized in our simulation. And finally, the macroscopic properties like the density and the velocity of the bulk fluid can be calculated by mapping the Lattice-Boltzmann onto a different equation which you want to represent. And there are some distinct identities to do that. Like I mentioned earlier, if you want to map Lattice-Boltzmann onto the Navier-Stokes, there are certain values, there are certain identities that need to be matched, from which you can find the macroscopic properties of the bulk fluid.
So for this part, we're going to talk about some of the examples on how to use the Lattice-Boltzmann method to solve um, diffusion equation problems. So first, we're going to talk about the hand calculation example. So this is the example of a heat diffusion problem. So we have copper rod with length of 4 meter heated on one side, and so that the first meter of the rod has the temperature of 400 Kelvin, and then the rest of the rod is at temperature 300 Kelvin, and then the heat source is removed for 3 hours. So we have to calculate the temperature distribution in the rod after 3 hours using the Lattice-Boltzmann method. So we're going to use this governing equation for the heat diffusion, in which we have phi as the temperature in Kelvin, and alpha is the thermal diffusion coefficient, which for copper is equal to 0.3996 meters squared per hour. And then the boundaries at the rod end are both. So first we have to uh, change the variables into dimensionless variables. Why we're doing this is to simplify our problem, so we can downscale the problem into a much simpler model, so we can actually calculate. We can actually use the Lattice-Boltzmann method to calculate by hand. So first we have x-axis, which is x divided by the length of the rod, and we have t-axis, which is t divided by the total time, and then capital letter T for the temperature. And then we go back to our heat diffusion equation, which is this following formula, and this is already in the dimensionless variables, and that's why we have alpha accent, which is equal to alpha times the total T divided by length L squared, which would give us 0.074925. So since this is a dimensional system, then if we downscale our model, then we should have the same amount of alpha accent. And in fact, if we go back to the equation and then we substitute with the downscale parameters, then we would have the same value of alpha, which is 0.3996. So we have to discretize our problem into, we're going to use D1Q3 lattices. So that means that it is one dimensional, and then for each of the lattices we are going to have three molecules. We would have the distribution function at 0, and then 1, which would go to the uh, positive direction, and then 2, which would go to the negative direction. So for D1Q3 model, then we would have these constants. CS squared will be equals to 1/3, and then W in the middle would be equals to 4/6, and then W1 would be 1/6, and then W2 would be 1/6, and then the velocity in the middle would be 0 because it would stay there, and then for the molecule 1 it would equals to 1, positive 1, to go to the positive direction, and then E2 would be equals to negative 1. And then to reproduce the heat diffusion equation, we would have these following identity equations. So the first one is the temperature will be equal to the sum of all of the distribution functions, and it will also equal to the sum of all of the function F equilibrium, and F equilibrium would be equals to W times the temperature, and then Fi will be equals to 0 for all of the nodes. And then for this problem we are going to use relaxation time tau, which equals to this formula, and would give us the value of 1.6988. So we have to calculate the initial temperature, dimensionless temperature for each of the lattice. We know that the temperature only the first lattice is affected by the initial temperature. So we would have 400 Kelvin, which would give us the dimensionless temperature of 1, and then the rest of the lattices are at 0. So first, to initialize the model, we have to assign the value of the initial distribution functions, which would be equals to the function equilibrium, and we know that F equilibrium is equals to W times the temperature. So that would give us the same value of the distribution functions and also the F equilibriums. So we have 2/3 for in the middle, and then 1/6 and 1/6, and only at the first lattice. And the next one is the collisions substep, which is represented by this formula. So from this formula we would get the updated value of the distribution function. We would call it f accent, and since fi equals to 0, then we could just cross out this part of the equation, so that would give us this formula. So we have the post-collision values as follows, and we will notice that this is the exact same value as the previous distribution functions, because we have the same value of fi and f equilibrium. Then the next step would be the streaming substep, So we would have these equations for each of the lattices and each of the molecules. So for the distribution function in the middle, that would be equals to that, also that particular distribution function, since it's not going anywhere. So we just update it with the new value. And then the for f1, uh, we would go backwards in the direction. So first we're going to update lattice number 4, the value f1 at lattice number 4, with the value from the lattice behind it, which is lattice number 3. And then after that we have to update f1 at lattice number 3 with the value at lattice number 2, and then update the value of lattice number 2 with the value of lattice number 1. And for f2 we would go in the opposite direction, so we update the value at the first lattice with the value from the second lattice, and then we update the second lattice with the third lattice, and so on until the end, until the last lattice. And we have to go in that particular direction because otherwise we would get mixed up in updating the value. So for again for f1 we have to go from the last lattice, and then for f2, which is the opposite direction, we will have to go from the first lattice. And then for the bounce back boundary conditions, we would update for the first lattice. For the west boundary, we have to update f1 with the value from f2. So because it goes, f2 goes in this direction, so it bounced back, so it became f1. And then for the east boundary at the fourth lattice, it would go the other direction. And so after we update the distribution functions after streaming, and this is at time step t(n) equals to 1/3, which means that t is equals to 1 hour, and we would have these values of distribution function. So after that we can calculate the temperature, both the dimensionless temperature and also the temperature in Kelvin at t equals 1/3, which is basically t is equals to the sum of all of the distribution function. We would have we can see that the temperature in lattice number 1 is now 5/6, and the lattice number 2 is 1/6. So we can see that the heat is traveling to lattice number 2 at this time step. And then next we just have to repeat all of the substeps: collisions, streaming, and the boundary condition substeps. So still at t(n) equals, at the time step equals to 1/3, we calculate the F equilibrium, which would give us these values, and then we carry out with the collision step to calculate the updated distribution function f(n). We would have these values. Then we carry out with the streaming and the boundary condition substeps at the next time step at t(n) equals to 2/3, and that would give us these updated distribution function values. And then the next one, we can calculate the we can calculate the temperature as well at that certain time step, and we can see that the at t(n) equals to 2/3 that the heat has traveled to the third lattice. And then again we calculate F equilibrium, and then we use that to calculate the F action after for the post collision distribution functions, which would give us these values. And then we carry out with the streaming and bounce back boundary conditions for Txm equals to 1, which is T equals to 3 hours. So this should be the our final results. We have the updated distribution functions as follows, and we can calculate the temperature for at the end of our 3 hours model. So we can see that the heat has traveled to the last lattice as in this particular example. So this should give you the idea of how this method, the lattice Boltzmann method, actually works to solve this particular heat division problem. But this is a simplified example, a simplified problem. So for the application, we actually will need to use computers to solve this kind of problem. So up next, we're going to discuss about some of the numerical example of the application of this method. So for this part, we're going to talk about the numerical example. We have already done the hand calculation example previously, and now we're going to discuss how to solve a similar problem by using MATLAB for this case. So we also have a heat division problem like the previous example, but this is, in a way, this is a simplified and also a more complicated problem example. So a slab is initially temperature equal to 0, which is T equals to 0, and then the left surface is subjected to high temperature and equals to T is equals to 1 at one end of the slab, and the slab length is in 100 units, and then we have to calculate the temperature distribution in the lab for T equals to 200, and the value of alpha is equals to 0.25. So this problem is already in dimensionless variables, so but it is in a way more complicated than the previous example, because we are going to discretize the model into 100 lattices, and then we are going to use 200 time steps for much more detailed results. So first of all, we are going to use D1Q3 LBM model, just like the previous example. And since we are using D1Q3, then we would have these constants, which are described here. So CS squared is equal to 1/3, and then W0 is 4/6 or 2/3, and then W1 and W2 is 1/6, and then M would be the number of the lattices. So we are using M equals to 101, but we are actually using 100 lattices. This will be explained later. And then for heat division equation, we would also have these identities. First, we would have T, which is equals to This is just for the dimensionless variables. So actually in this certain source code, the temperature is described as rho, but it should be phi, but that doesn't really matter, so we just call it rho, but just so that you have the idea, rho is the temperature. And then we also have the distribution functions. We have 3 distribution functions in each of the lattices. So next we are still in the initialization substep. So first we have to discretize this lab into 100 lattices. I equals to 1 to m minus 1. M is 101 minus 1, so we have 100 lattices, and each of the lattices would have the length of 1 unit. And then we already know that alpha is equals to 0.25, and from since we know alpha, we can determine the collision operator omega by using this formula. And this is a bit different than the example that we have done for the hand calculation, because we were using the relaxation time tau, but for this case we are going to use the collision operator omega. We know that omega and tau, we could go back and forth from omega to tau, so um, it won't really affect our results. So yeah, we're going to use omega for this case. And then we know that the temperature at the boundary is equals to 1. This is where the heat source is. And then we are going to use a 200 time step. And to initialize our model, the distribution function would be equals to F equilibrium, and we know that F equilibrium is equals to W times the temperature, so that would give us these values for the distribution function. So the next step is the collisions substep, which is described by this equation, this formula. And so for the collisions, streaming, and also the boundary condition substeps, we are going to do it for 200 time steps. So yeah, 1 to n step, the number of the time steps. And then so for the first one, we have to calculate the F equilibrium for each of the molecules, and for the molecules in the middle we would have to use W0. And then for the value for F1 equilibrium and also F2 equilibrium, we would have the same values because W1 and W2 is the same, so we can just use FEQ. So yeah, we are going to update the distribution functions for this particular substep. This would give us the post-collision distribution functions. And then the next one is the streaming substep, which is given by this formula. And again, remember that we have to do it in this particular order for each of the distribution functions. For F1, we have to start with the last lattice. We update it with the value from the lattice right next to it, and then after that we update that distribution function with the value from the lattice behind it, and so on. And for F2, since it's going to the opposite direction, then we'll have to start with the first lattice and then update it with the value of the second lattice, and so on. So that's why for F1 we would have the m minus I plus 1, which would give us the last lattice, the lattice at the very end, at the east end, you might say, and that will be updated with the value of f1 at m minus I, which is right next to it. And then for f2, we would first update the value of f2 at I, which is at the first lattice, and that will be equal to the f2 at the lattice right next to it. And then for the boundary condition, we know that at one end we're going to have T wall, which is a constant temperature heat source. So that will be in lattice number 1, and then at lattice M, or lattice at the very end, we would have this bounce back boundary conditions. So after we update all of the distribution functions, we could get the temperature, which is rho, which is equals to the sum of all of the distribution functions. So the source code will repeat all of those steps until time step equals 200, and that would give us this result. So this is the temperature distribution for at time step equals to 200. So we can see that at x equals to 0, the temperature is 1 because that is where the heat source is, and the temperature at x equals 100, or the other end, uh, it would be the least affected by the heat source. So yeah, this example should give you the idea of how lattice Boltzmann method actually works to solve heat diffusion.
The Lattice-Boltzmann method has endless applications throughout science, engineering, and technology. In our domain, it has been used in oil-water displacement in porous media to model the fingering phenomena. In medicine, it has been used in blood flow modeling, the modeling of air in lungs. It has also been used in urban planning and traffic management, in meteorology, in atmospheric turbulence, in washing machines, in filtration systems, etc. Uh, well, over here we can see a air conditioning unit in two different configurations. Either it's fixed or it's rotating. So we are able to model the two without the need of placing them there physically, and we can tell which one is better able to cool the room. Using Lattice-Boltzmann method, this was modeled. In the second one, we have a water column which is falling, and this has been modeled using the Lattice-Boltzmann method, which you can see now. Very accurately done, without the need of ever doing this actually in reality. Well, that's why this is called a simulation. Just look how accurately this has been done. Amazing. So in the next one, in this simulation we have a clot in a washing machine, and we're ensuring that this clot is not torn apart due to the forces within the water. So Lattice-Boltzmann method was used to model the velocities of water within the washing machine, and we were able to like optimize, figure out where so that we never tear apart the cloth. I hope you were able to understand about the Lattice Boltzmann method, so feel free to do the quiz on Canvas now. Thank you.